Alright, good morning everyone. Today we are going to continue exploring our MicroDev series of development boards. We are going to take a deeper dive into the schematics and the PCBs of these development boards. We're back again in the ESP32-S freeze schematic, since this is the most advanced board. We've got the Wi-Fi antenna and so on going on, but as we've already said, the power stage or the power block of all of these MicroDev boards are exactly the same. So we are in the top left corner of the schematic, where we always seem to find our power stage. We can see our USB-C port here. It has two 5.1K resistors connected to the CC1 line and to the CC2 line. This is to trick any USB power delivery capable device or supply to give us free amps. This is a neat little trick that you can use for any circuit where you would like to get 3.3 amps delivered to you from a USB PD source. Other than that, we do have our two data lines, USB D+, USB D-. These, together with the V-bus line, the 5 volt supply, the 5 volt USB supply, are connected to this little IC. It's a constellation of diodes and TVS diodes. These are of course ESD protection diodes. We've chosen this part here, this USB LC6-2P6, since it is very small. It also incorporates protection for both the data lines and the V-bus line, the USB power line. However, we do not have any protection on our CC lines, which might be questionable, but the reason for this is of course that we are very limited in space. So therefore we omitted the ESD protection for these two lines, and they are also only connected to a pair of resistors, which are hopefully not as sensitive as the data lines that goes directly to our microcontroller. Alright, so let's take a look at the datasheet for this part now. Okay. We are in the datasheet for the USB LC6-2P6. We can see here in the features that we are compliant to a bunch of ESD standards. Air discharge plus minus 30 kilovolts, that's nice. Even some lightning stuff going on here. Also we see this is a tiny package, it's a SOT 666 package. Also, we are getting reassured down here in the typical applications, where we see that this is usually used for USB 2.0 power and data lines, which is exactly what we do. One particular reason that this device is well suited for use with these kind of high-speed communication protocols is because it has a very low junction capacitance, which is good when you do not want to distort your signals, especially for USB. We do even have some recommendations here. If we jump over to this application note from Texas Instrument, we can see here, for instance, for USB 1.1, which is the actual speed that the ESP32 can output, but it's not the standard that follows. We can see here that a capacitance less than 20 picofarads is recommended to support this signal speed, which means that we do not want more than 20 picofarads of capacitance on our USB line. Otherwise, we might start to end up with some signal integrity issues and so on. And if we go down here to USB 2.0, then we can also see here for capacitance. Now, okay, then again, we're not reaching these speeds, the ESP can't reach these speeds, but here the recommended capacitance is even less, only 4 picofarads. Now, before we leave the USB, we still have one thing left to talk about, and that is impedance matching and placement of our protection device. So let's start off with the placement of our protection device. We'll go into the PCB layout and we will zoom in down here on our USB port. we can try to hide our zones to make it a little bit more visible, and maybe perhaps even remove some silk screen like that. Okay, so here we can see our USB port, and up here we find our protection device. And as you can see, we've placed this as close as possible to our USB port. Now the data lines, they go directly from these pins here into the protection device, and the USB power line comes partly from the top but also from the bottom layers into this point here. So we're doing this because we want to avoid any potential ESD spikes or lightning spikes or voltage spikes in general to make its way into the PCB and start to disturb a bunch of other circuitry. So you always want to try to place your protection devices and filter devices as close as possible to the connector or to the pin which they are protecting. Now let's talk impedance matching, and specifically impedance matching for our USB trace. Now impedance matching is something you do when you want to remove or avoid reflections in your high-speed traces. If you don't do this, you might not be able to run your high-speed traces at the desired data transfer speed. And in our case, the ESP32 is able to communicate at 12 megabits, which corresponds to roughly 12 megahertz. So we're going to try to impedance match our USB data lines for this here. Now, before we start, let's just say that when you have very short traces, like we have here, you don't really need to do this, if I'm going to be honest. You're most likely going to be fine with using your regular trace width that you've been using for all the traces. But just as an exercise in diligence, we are actually going to match these to the best of our ability. So how do you do that then? Well, you play around with the thickness of the trace, and you play around with the spacing of the trace for a differential pair. And KiCad has a built-in tool for this. It's called the calculator tool. And in this tool you could go down to transmission lines, and then you'll end up at this page. And here you can select different types of transmission lines. For the USB, it's a differential pair. We're going to have to use a coupled microstrip line, as we can see here, two traces close to each other. But you also have the classic microstrip line, or as we'll see later on with the antenna for the ESP, the coplanar waveguide. But the coupled microstrip line is what we're going to use now. We have a few parameters here to fill in. First off, we have the substrate parameters. Most of these parameters you can get from your manufacturer. For instance, the dielectric constant is of course going to be based on your substrate, or if you're using FR4 or what type of prepeg you have. And KiCad actually has a few of these built in. He, for instance, has the FR4 one here. You could go and use a general FR4 dielectric constant, or perhaps you're using Rogers and you could go in and use a standard Rogers dielectric constant. But for our case, for the MicroDev boards, we are actually using a specific stack up from JLC PCB, and we can find this data if we go to their website and check out their multi-layer precision PCBs with impedance control. And here they are kind enough to give us the information we're actually looking for. Now, before we start, this information was not available to us when we initially designed the MicroDev boards, so our impedance matching is actually a little bit off, which we'll see at the end here. But let's have a look here. Here are all the different 4-layer control stackups that JLC is offering, and we are using this one, number 2, basically the bare bones 7628 stackup. That's the prepeg. So from this table here, and also from this table here, we can get most of the information we need. We can see here the 7628 prepeg has a dielectric constant of 4.4. So we'll input 4.4 here. Now for the dissipation factor, this one we do not unfortunately get, but we can use a ballpark value here. It doesn't affect stuff as much, so it's not super critical. Typical values are somewhere in the range of 0.02 and maybe 0.16 or 0.14. We'll keep this at 0.02. After that, we have the electric resistivity of our conductor. Our conductor in this case is of course going to be copper. We have copper layers, so we can go in here and just select this value for copper here from the built-in KiCad parameters. And then we also need the height from the ground layer to the traces themselves. So then we'll have to go into this table here. We said we were using this stack up, and we can see then here the thickness of our prepeg is 0.2104, and we are going to route our USB traces on the top layer, and our first internal ground layer, this L2 layer, is going to be a solid ground layer in the MicroDev board. We can actually go and confirm this. So we see here USB traces are on the red layer. The red layer is the top layer. Now if we enable zones and we go into the green layer, which is our solid ground plane, we can see that yes, it is indeed a solid ground plane. Great. Then we know what parameters to use. We're going to use the prepeg, which is this one, which we have already filled in here. And then we have the height of box top. This is not important. We're not going to take HT into account. But we are going to take our thickness into account, which is the thickness of our copper trace. Now, our copper trace is, you can see here from the stack up, it is 0.035 millimeters, which we entered here. We're not going to consider roughness of our surface, and our conductor's permeability is basically going to be 1. That's copper for you. So this one is almost always 1. After that, we need to input our operating frequency. And for our USB line that runs at 12 megabits per second, that's roughly going to be 12 megahertz. So we'll input 12 megahertz here. Now we can play around with our physical parameters. We can play around with the width, the spacing, and also the length. And when we play around with these values, we'll press analyze, and that will give us a value down here that tells you the differential impedance. And for USB, you're looking for 90 ohms differential impedance. And as you can see here, 0.33 would basically give us dead on 90 ohms, which would be really nice. Exactly what we want. So let's go and have a look at our USB traces. And unfortunately, we will see that our traces are actually 0.3 millimeters. And as we said before, that is because the information that's available now from JLC PCB was not available when we first started developing these boards, and so we are a bit mismatched right now, unfortunately. I think we used something, the information we were able to get was something like this, I think 4.6 for the dielectric constant, which then sort of would make this value undershoot, but if you go up to 0.3 you end up closer to 90 ohms, but still a bit over. Perhaps it was even larger. In any case, this is this is wrong. So in a future revision, we are going to correct the width of our USB line. So we're done with the USB. Let's continue on with our automatic power switch here. Now the automatic power switch, as we said, is a pretty simple circuit. It consists of only 3 components. We have a P-channel MOSFET here in the bottom. We have a 100K pull-down resistor, and we have a Schottky diode up here. We're using a Schottky diode here just to try to minimize power losses, since Schottky diodes have less forward voltage than regular diodes, generally speaking. You could probably use a regular diode here if you wanted to, but we chose to go with a Schottky one here. Now, let's try to explain how this circuit works in very basic terms. This is, as we said, a P-channel MOSFET. P-channel MOSFETs work sort of in the reverse to N-channel MOSFETs. If you have a low voltage at the gate, the P-channel MOSFET will conduct. If you have a high voltage at the gate, the P-channel MOSFET will not conduct. Right? So what happens then when we have our USB cable plugged in here and we receive 5 volts here on the VUSB line? Well, yes, then the gate here will see a high voltage, and as such it will not conduct. so we will only receive power from the USB. Now, if the USB was not connected, we have this pull-down resistor, which will pull down the gate to ground, i.e. presenting a low voltage to our gate here at the MOSFET, and as such turning it on, allowing power to flow in through the V-in pin. Now, there are also another benefit of having the MOSFET or having the V-in pin here as the secondary input source, since we want these MicroDev boards to be used with batteries, or we suspect that they're going to be used in a lot of battery powered applications since they are so small. We don't really want the battery power to enter here through this diode, since, as we said, it's going to dissipate quite a bit of power. However, the MOSFET on the other hand only has an RDS on of about 47 milliohms, which is very small, which means this guy will not dissipate much power when we feed power through here or current through here, i.e. this makes it more power efficient when we run our MicroDev board off from a battery on the V-in pin rather than from the VUSB line. Speaking about batteries, we wanted the MicroDev boards to be well suited for battery powered applications. Since they are so small, it is very likely that they are going to be used in battery powered applications. As such, we made sure that the V-in pin is connected to the MOSFET and not to this series diode, since, as we said, this guy will not dissipate much power at all when it's turned on. Also, the linear regulators here need to be able to handle the voltage from a one-cell battery. As we can see here, max 7 volts. This is also from the datasheet of these devices. We'll take a look at these in a second. If we jump over to the datasheet for the MicroDev ESP32S3, we have the specifications for the V-in pin here, and we can see that we've spec'd it from 3.5 to 6.5 volts, which should cover most of your lithium batteries capacity. If we look at a few characteristic curves here, this is a characteristic discharge curve for a lithium LiPo battery at 0.5 C, and we can see here 3.5 volts would be somewhere here in the middle, and as we can see here, across temperature, or at least across minus 10 degrees Celsius to 50 degrees Celsius for this particular battery, we do basically use all of the power available in the battery. It's first, once we've discharged about 80% of the battery's capacity, then yes, the knee starts to appear, and we will cut off here somewhere, or the circuitry will stop working. The same goes for Li-ion battery. Here is a characteristic discharge curve for a Li-ion battery, and we can see here 3.5 volts covers most of this battery. Now, lastly, for the power block, we have our two linear regulators. These are actually LDOs, low dropout regulators. We chose these because of their small size and also because of their enable signal, which allows the microcontroller to turn on and off the auxiliary regulator, this bottom one here. They, of course, have their decoupling capacitors, and they also share one. They have their output filtering capacitors, and also the enable pin is pulled down with a fairly large pull down resistor. Now let's take a look at the datasheet for these guys and see what they're spec'd at. Here we are in the VL9005's series datasheet. These regulators come with various output voltage, of course, as they usually do, but you can see here they have a fairly narrow input voltage range, and their maximum output current is about 500 milliamps, which is the minimum requirement for the ESP when it is doing its Wi-Fi stuff. We also see here the packages are fairly small, all of the variants. We'll go down here again, our input voltage 2 volts to 7 volts, our maximum output current at 500 milliamps. We see here our dropout voltage at 200 milliamps, we drop about 220 millivolts, which is kind of nice. Now let's finish off by having a look at the layout one more time. So we've managed to cramp all of our power circuitry down here in the bottom of the PCB, and as we've said many times before, this is identical on all the MicroDev boards. We have the USB, we've looked at that already. We have our CC resistors, we have the MOSFET for the automatic power switch. Over here we have the first decoupling capacitor for the incoming USB. Over here are our two regulators with their respective decoupling capacitors placed as close as possible. As you guys can see, we've tried to keep traces as short as possible. We've also utilized the bottom and the top layer to route our USB power. Let's jump over to the bottom layer here, for instance. Maybe this is a bit hard to see, but this entire block here is our incoming USB line. This allows us to easily route out to the protection circuitry and also feed the automatic power switch and the regulators. And that's about it. It's not that complicated, the input circuitry here. It's pretty basic, bog standard. Let's finish off by having a 3D view, a nice 3D view. Everyone loves a nice 3D view. Here we can see the components in all their 3D glory. Our small regulators here, very small, very nice. A good tip for all of your tiny projects or battery power projects that you want to do. Alright, thank you so much for watching, and we'll see you again next time. Bye bye.